Hey everyone, welcome back to Wrath of Math. Hope you're doing well on this jolly, lovely Christmas Eve. This is not a typical video, so if you're here for highly concentrated math instruction like I typically try to provide, this is not the video for you. Go check out some other video. This is going to be a long, drawn-out video. I'm not sure how long it's going to be. I would guess probably around an hour. I suppose we'll see. Kind of hope it's not that long because I'll probably get winded. I'd show you, I'd move the camera and I'd point it outside, see the beautiful night to show you that it is indeed nighttime, just to set the mood, but it's, then I'd have to put the camera back in its proper position. Oh, and what a pain that is. But it is Christmas Eve. We got that Christmas Eve vibe. I'm wearing this sweatshirt that's too big for me. It's got that cozy feel. I'm wearing my pajama pants. I got hot chocolate. I got a thing of tea to get me through this long video, keep me hydrated, and I got a bunch of comments teed up. I'm both grateful and sad for it to now pretty much be at the point where Wrath of Math gets too many comments for me to respond to them all. And there's a lot of comments I haven't had the chance to respond to lately. So I thought I got this sort of last minute idea. I thought a fun video here for Christmas Eve would be to take a look at some of the comments I've missed recently and respond to a bunch of them. I thought that would be a lot of fun, and I hope you guys will enjoy that. Put it on in the background, just listen to me drone on about math for an hour, sit back, relax, grab a cup of hot chocolate like I've got, and we'll just enjoy another splendid night, another splendid Christmas Eve this year as 2019 comes to a close. I suppose, without further ado, I should go check out the first comment. If I had planned this further ahead, I would have printed out the comments or something, but I'm going to have to walk to the computer to read them, and I'll put the comments up on screen. Good thing I can do this because I got a wireless microphone now. All right, first comment that I got to respond to here from Atul Gupta asked how to find the number of subsets of any given set that contain a particular number or more than one particular number of elements. And it gives an example. The set A contains the elements 1 through 8. And we got two types of problems here. Find the number of subsets of A containing 1 and 2. And find the number of subsets of A containing 1, as well as the number of subsets of A containing 2. I think that's the problem. Man, this thing squeaks so loud. I sure hope there's no big audio problems while I'm recording. Otherwise, might have to trash the entire video. So thanks a lot for your comment, Atul Gupta. Thanks for the question. Let's see the solution. So the first thing, let's write our set A. A contains the elements 1, 2, 3, 4, 5, 6, 7, and 8. And we're going to take things real relaxed this video. I'm probably not even going to speed anything up in my editing. Sometimes if I have to write out a lot, I speed it up in the editing so you don't have to sit through that. The point of this video is sitting through and blabbing, so no speeding stuff up after the fact. So we got to enjoy writing out all 8 elements of A. So we want to know how many subsets of A contain the element 1, right? So we'll say this is question 1. How many subsets of A contain the element 1? Well, many of you may know, some of my most viewed videos are on set theory, so a lot of my subscribers know the number of subsets of a set is 2 to the power of n, where n is the cardinality of the set. How do we come to that conclusion? Well, because when we're creating a subset, suppose we're creating a subset of A, we have 2 options for each element, right? We could either include 1 or not include 1. And then for each of those 2 choices, we have 2 choices for 2. We could include 2 or not include 2, and so on. We got 2 choices for all of these, in this case, 8 elements. We can very simply answer your question with the same logic. So we want to know how many subsets of A include 1, right? We can use the same logic, except now for 1, we don't have 2 choices anymore. We only have 1 choice because we're saying we are going to include it. We're going to include 1. And so then the total number of subsets becomes 2 times 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 that 1. So A did have 2 to the 8 total subsets, but since we're saying we are going to include that one element 1, there are 2 to the power of 7 subsets of A that include 1. and say it's going to be the same answer for 2, right? If we say we need to include 2, how many subsets include 2? Well then, if we're not forced to include 1, we have 2 choices for 1, then we only have 1 choice for 2. And so again, the answer is 2 to the power of 7. Suppose we want to know how many subsets include 1 and 2, which is almost your next question. Then we just have 1 choice for both 1 and 2. 1 times 1 times 2 times 2 times 2, and the answer becomes 2 to the power of 6. So there's a sort of general solution going on there for the number of subsets of a set where you want the subset to include a certain number of elements. You can think about that more if, this is a problem that you have to do a lot. If you have to do this type of problem a lot, we could solve it in the more general case, but I think you see what I'm getting at here. And now let's check out the second half of your comment. You were asking, if I recall correctly, because I can't read it from here, how many subsets of A include 1 and 2, but only have 4 elements, right? So this is close to just... Well, this is going to be a combinations question. You might be familiar with combinations from combinatorics. So let's start with how many elements of A contain, how many subsets of A contain 4 elements? Well, it would just be the number of elements of A, 8, choose 4. This is a binomial coefficient, if you're not familiar with this. It's equal to 8 factorial, the top number, divided by 8 minus 4 factorial, the top number minus the bottom number factorial, multiplied by 4 factorial. That's the number of ways we can pick 4 elements from this set of 8 elements to include in a subset. So the total number of subsets with 4 elements is 8 choose 4. However, this is not the solution to your question because we don't have 8 elements to choose from, and we don't have to choose 4 elements. Why is that? Well, because in your question, if I recall correctly, you're saying that all of our subsets with 4 elements will include 1 and 2. So how many total options are there? Well, now it's no longer 8 choose 4. Now we only have 6 elements to choose from because we've already said that we're going to include 1 and 2. So we have 6 elements to choose from, the other 6 besides 1 and 2. And then since we want our subset to have 4 elements total, but it already has 1 and 2, we only need to choose 2 more elements. And so the total number of subsets of A containing 1 and 2 and 4 elements total is 6 choose 2, which is 6 factorial divided by 6 minus 2 factorial multiplied by 2 factorial, which, let's go ahead and simplify this, is equal to 6 factorial divided by 6 minus 2 factorial, that's 4 factorial, times 2 factorial. 6 factorial divided by 4 factorial is going to leave us with 6 times 5 in the numerator, divided by 2 times 1 in the denominator, that's 2 factorial. So this is 6 times 5 is 30, divided by 2 is 15. 15 total subsets of A that have 4 elements, including 1 and 2. So pretty fun little problems, fun sort of counting problems. And I don't expect all of my instruction in this big video to be as clear as it usually is. I'll try to be as clear as possible, but I'm not going to dwell on every single point. So, I'm trying to knock out all these comments. So we got to keep things moving. So I didn't explain factorials, which is something I might typically explain in a normal lesson. We're going to move on. All right. Now, I tell you, I clean this whiteboard as much as I want, and it just looks filthy after I erase it. It just spreads the black marks all over the whiteboard. Gonna get a good workout erasing this whiteboard over and over again. If I don't speed up videos, if I don't speed up this video when I'm editing it, you'll have to listen to me drink that hot chocolate, and I happen to be a loud swallower. Maybe I'll do more editing than I initially thought. All right, second comment. And excuse me for however bad I pronounce some of these names. YANDRAPU Kumar asks, this is on my video on how to find the diagonal length of a rectangle. He asks, for example, sir, A has a length of 2.447 and B has a length of 1.515, so how to find C. Okay, so, some of these comments are a little bit vague. I'm not totally sure exactly what you're asking, but I think I know. So let me go ahead and we'll figure this out. So I think the question is, we have a rectangle. We've got a rectangle with a side A and a side B. That's a rough rectangle. Let's try that again. Right there, right? We've got one side, the longer side, that he called A, had a length of 2 point something. What was it? 2.447. 2.447. And then the shorter side, B, had a length of 1.515, I think. 1.515 units. Yeah. So the units don't matter, centimeters, inches, miles, kilometers, light years, whatever you want. Then the question is, how do we find C? How do we find this diagonal? Or this diagonal? Doesn't matter. They're both the same, which you could prove using side angle side, triangle congruency postulate. So this is a rectangle, so that's a right angle, that's a right angle. These are right triangles, so we use the Pythagorean theorem. To find C, guess I'll switch colors here to more precisely identify what I'm talking about. To find C, the length of this diagonal, or again the other diagonal, they're congruent, so it doesn't matter which one we try to find. We just use the Pythagorean theorem. So 1.515 squared plus 2.447 squared is equal to C squared. And so, working with this equation a bit, we can solve for C to find the length of the diagonal. Again, the Pythagorean theorem tells us that in a right triangle, the sum of the squares of the legs is equal to the square of the hypotenuse. Beautiful. If you've never seen a proof of the Pythagorean theorem, there are tons of them, lots of beautiful, easy to understand proofs. I'm actually thinking, I haven't recorded it yet, but for my Christmas night video, because I want to release a video on Christmas morning and Christmas night, just having a blast, it's going to be a proof of the Pythagorean theorem, a fun proof. So if you want to see a proof of the Pythagorean theorem, check out the video coming out tomorrow night. That'll be a lot of fun. So 1.515 squared, yeah, I'll solve this, but I'm going to have to go grab my calculator, and I can continue to talk to the microphone because I got this wireless microphone set up. Let's see, I'm going out in the kitchen, got to get my financial calculator because that's all I've been using lately. Sure, the audio quality's getting all weird now. All right, got my BA2 Plus financial calculator. Whew, let's solve for C. 1.515 squared, about, I don't know if the camera can see that, it's about 2.295. I'm going to put this in my mouth. Up. 2.447 squared is about, see that there, about 5.988. About 5.988. This is equal to C squared. Add those two numbers together. We get that C squared, and this is only approximately, right, because we had to approximate. So C squared, adding these two numbers together, is approximately 8.28. Take the square root of both sides. C is approximately, that's a 2.878. So C is about 2.878. 2.878 units, whatever those units may be. And that's the answer to your question. Don't know if we'll need the calculator again, but I'll set it aside so can grab it in a moment's notice if we need to. And might be able to answer the next comment over there. We'll see. What do we got? Let me take a sip of tea. Whew. It's not expired yet, but I bought it like a while ago. It says it's good till December 30th, so we're good. All right, what's next? Kathy Nenni asked me, so what's x equal to? That's one of those questions where I'm going to have to click on the video real quick to see. I took a glance at this earlier, so I kind of know what you're talking about. Let me jump to the video to see what we got going on here. And I got to watch an ad. Got to watch an ad before the video. All right, skip the ad. I don't need the money. And what do we got going on here? So the reason you want to know what x is equal to, in the video, the point of the video, it was a video on using the distributive property with fractions. The point of the video was not to solve an equation, right? It wasn't, that wasn't the point. The point was just practicing using the distributive property. So we didn't set the equation in the video equal to anything to solve for x. but we can go ahead and do that, and just for practice, and solve for x. So let's do that. I'm gonna write in pink. So the equation we started with in the video, try to fit this on the board so I don't have to erase so much. We started with 3/4 multiplied by x plus 8. I think this was a viewer requested video, if I remember correctly. It was in 2017. Geez, over two years ago. Wow. Okay, so all we got to do, let's set this equal to something, right? How about, what do you want? What do you want to set it equal to? How about 13? Let's set it equal to 13. 13's cool, nice prime number. Okay, so now here in this situation, I would not use the distributive property because we can just get rid of the 3/4. Bring it over here by doing some division and multiplication. No need to do the distributive property here. So what I would do is multiply both sides by 4 to get rid of that 4 in the denominator. Also, if you're comfortable with it, you could just divide both sides by the fraction 3/4. Let's take it slow, do it in 2 steps. Multiply both sides by 4 to get rid of that 4. We're left on the left. We're left with, on the left side of the equation, 3 times x plus 8 is equal to 13 times 4, which is 52. Then divide both sides by 3. So x plus 8 is equal to 52 divided by 3. I know that 52 is not divisible by 3 because 5 plus 2 is 7, which is not divisible by 3. Then we just have to subtract 8 from both sides to solve for x. X is equal to 52 divided by 3 minus 8. I'm going to write 8 in terms of thirds. So 8 is equal to 24 thirds. Then we can go straight into the subtraction here. 52 minus 24 is going to be 28. 28 divided by 3. And unfortunately, we don't get something that simplifies beautifully at the end. It's too bad. For a second, I thought we might get something pretty, but that's all right. 28 thirds is fine. Just a beautiful rational number, as beautiful as any other. So in this case, that's what x is equal to. But yeah, in the original video, there was no solving for x because we didn't have it set equal to anything. You could have graphed a line with that equation, this one here, but and on that line, you would have seen that when x equals 28 thirds, which I'm sure is the first point you would have checked, when x equals 28 thirds, y would be equal to 13. And so 28 thirds, that's about 9.333 repeating. All right, now I guess I have to erase this. The train is blasting outside. I don't know if it blasts at the same time every night or when it blasts. I'd like to go outside sometime and follow its sound, go find where the train is and see it. I always think it's kind of cool watching trains pass by. It's like, man, it's kind of like going back in time. Do you imagine just sitting on a train, you know? I took a train ride to the North Pole. It was a sort of, fun ride for kids years and years ago on an actual train. And what a great mood they had on that train. It was a lot of fun. All right, next comment. Having some good fun here, running out of breath. Let's see. Got to go back. And the next comment is, blah, blah, blah. Does matter matter on my video, is 0 even or odd? Which I think is one of my more disliked videos. He's got a long one. Let me take a breath. He says, and thank you for commenting, thank you for watching. He says, I know I'm really late, but I have an issue with this argument. I'm not very math inclined, and I've yet to learn this stuff in school, so I'm pretty clueless about the math. But the basic concept of even numbers is basically that when split in half, it has the same value on both sides. 0 lacks a value. I want to interject here and say that description of even numbers, I know what you're saying, but I think that's a slightly careless way to word it. Let me continue reading the comment. Therefore, shouldn't this not be even nor odd, like a neutral number? Of course, you could prove it algebraically, but who's to say zeros don't follow the same rules of other numbers? As even though 0 lacks a value, when split in half, it would still be 0 and 0, but in my head, 0 is the lack of a number. It's more of a placeholder. It seems to me that 0 should be neither even nor odd. I know saying all this makes me look like an idiot, but I'm only on 8th grade math level, so be easy on me in the fact that I'm ignorant. I'm probably all wrong, so please feel free to be extremely critical with everything I said. I'd appreciate it. I love learning from my mistakes. Does matter matter? You certainly do not sound like an idiot, quite the contrary. You sound like you've got an active mathematical mind. You're trying to reconcile, new information with what you already know and your current understanding of things. And that's good. That's a mark of a sharp mind. You sound very smart to me. And I appreciate the really well put comment, really great comment. And it's a great question. So the first thing I would say, which I think you pointed out in your comment, is that zero, to me, zero does follow the description of even numbers you were getting at. But what you said is that an even number is a number that you can split in half, and it's got the same value on both sides. But we can do that with any number, which is why I say that's just a little bit careless, right? So if we have like 1, for example, which is an odd number, we could split it in half and have 1/2 on both sides. But I know what you're saying. You're saying an even number is a number we can split in half so that it has the same number of whole units on either side, all right? So with an odd number, for another example, if we take 3, we could split it into 2 on one side and 1 on the other side, or if we wanted to split it perfectly in half, we'd have to split it with 1.5 on one side and 1.5 on the other. Whereas an even number can be split with whole units on either side. So I understand what you were saying. And yeah, like I think you touched on in your comment, is that 0 follows this description perfectly well. Man, that's filthy. If we take nothing, like what's on this whiteboard now, we can split it and we have nothing on either side. So 0 fits that description of an even number. And as far as whether or not 0 lacks a value, to me, I feel like 0 is a value. It's a really important value. It's not just a placeholder. Obviously, it sort of acts that way in our number system, which really helps us communicate the numbers. But conceptually, it's not a placeholder. Conceptually, it's a really important thing. You could kind of say that any digit is a placeholder, 2 is a placeholder for the idea of 2, this sort of abstract idea, this thing called a number. But I feel sometimes our basic understandings, our sort of intuitive understanding of things, like your understanding of an even number, gets sort of, at certain points, it starts to become not so obvious how our understanding applies to certain cases, like, can you really split 0 evenly in half and have the same number on either side? And for those sort of tricky, same thing with negative numbers, right? Can you really split a negative number in half and have the same number on either side? Does that make sense like it does with a positive number? There are numbers where it's not totally obvious how our basic understanding of something should apply, which is why we need more rigorous, generalized definitions that we can always sort of apply in an ironclad way and see for sure, no matter what we think or what we feel should be true, we can let the definition speak for itself and see what is true based on that definition. If we don't like what the definition leads to, we can change it. Math is set up and propped up by the axioms we choose to accept and the definitions. We create a definition for something and it sort of takes on a life of its own and it takes on truths that it takes us time to discover, but it's up to us to pick the definitions. What's this word gonna mean? It's sort of up to us to pick it. So like 1 used to be a prime number a long time ago, but that got kind of annoying because every time many theorems that would be proved about prime numbers, many theorems that would be proven, you had to exclude 1. So at a certain point, it comes, 1's kind of weird anyway. It's getting excluded from all these prime number theorems. Let's just say it's not a prime number and save us all the hassle. So anyways, yeah, and I'm going to show you a really cool example now that again are what's intuitive and what is helpful. These sort of basic understandings of things like even numbers and whatnot, they're helpful and they're a good place to start. But at a certain point, sometimes we need to get more rigorous, like with our definition of even numbers, where we say, I'll keep the pink, I guess. We say numbers even, say n is even if it can be written as 2k for some integer k, right? This is what I say in the video on if 0 is even or odd. At least I assume it's what I say. I haven't watched it in some time. And so 0 is even because it can be written or because it's equal to 2 times some integer, the integer 0. So 0 fits the definition of an even number. just like negative even numbers do. They can be written as 2. Negative 4 is equal to 2 times negative 2, which is 2 times an integer, so it's even. Let's see a cooler example of what I'm talking about, though, where we can sort of start off with a really fun and intuitive basic understanding, but we need to get more rigorous. You know, eventually we need to get more rigorous. Let's check it out. So consider x squared, right? I'm not sure if you've done graphing before. I don't know when people learn different things. But if we graph x squared on the xy plane, it looks like this, right? So this is the x-axis. So for any given x value, let me change the color here. For any given x value, some x value here we could just call, forgive my overuse of the symbol, but I'm just going to call it x. We're just going to call it x. Some x value x, the number up here on this graph of the function, this is x squared, this sort of purple point here. Now, another way we could represent x squared is with a square, right? Because the area of a square with side lengths x is x squared. This square's side lengths x, its area is x squared. So say we want to know how much the value of x squared changes with a tiny little change in x. We could use this beautiful little square to get an idea of how x squared changes with a tiny change in x. Let me change colors again to red. Right, so we got this value. We got this value x and x squared, which is the square of x. How will x squared change if we go forward just a little bit? Say we go forward to x, say we go up some number, we'll call it dx for difference in x. So we go up to some x plus dx. How does x squared change? Again, we can figure that out using the square. So let's increase both the side lengths by that dx, that difference in x, that amount that we're changing. So we'll add that length to both sides. Dx, that red part there, and dx, that red part there. Think those are close to equal. And then we can finish drawing this around. Looks something like this, and you can see by extending both sides of the square by this little difference, dx, we've got the total area of this square has 3 pieces, 3 new pieces, I should say. This skinny rectangle, and this teensy tiny square in the top right, which has dimensions dx, right? dx by dx. So the total change in area is the sum of the area of this rectangle and this little square, right? That's how much the area increased. Now, if dx is really, really tiny, this little square on the top right is going to be negligible because it's a really, really tiny number times a really, really tiny number. If dx, for example, if we changed by 0.00001 units, the area of this square, this number squared, is going to be super, super tiny. So suppose we just ignore that, right? And we'll get a pretty close approximation to the total change in area, which is just the sum of these 2 rectangles. That's how much the area will have changed. Just moving my mouse here to keep the computer awake. Don't want it to fall asleep. Okay. So what's the area of these 2 rectangles? Well, this length here is x, right? It's x. Same thing over here. This length is x. So the total area of these 2 rectangles is x times dx plus x times dx, because there's 2 of these rectangles, right? Again, dx is going to be a really small number because we're interested in how x squared changes with really tiny changes in x. So square that tiny change, which is the area of this square, super tiny. So let's forget about it. We don't need it. X dx plus x dx is equal to 2x dx. So this tells us if we change, if we change by this tiny number dx, right? So we go from looking at x squared to x plus dx squared. The total change in that squared value will be about 2x for, whatever value x happens to be, times that tiny change dx. And you can verify that this is pretty close to accurate. It's a very good approximation by plugging in some numbers yourself, which I won't do now because we've got to get on to other comments. But as that difference, as that little change dx gets smaller and smaller and smaller, this approximation is going to approach the exact truth. This is calculus. This is called the derivative of x squared, which gives us a sort of hypothetical instantaneous rate of change. So if we plug in x equals 3, we'd get 6 dx, and that's the rate of change of x squared at the moment that x equals 3. It's really cool stuff. This is just sort of a, surface level look at the derivative of x squared. We can use an argument like this to find the derivative of x cubed. We just need to have the artistic skills to draw well in 3 dimensions. But once you go up to 4 dimensions, a drawing like this, a cute little diagram, isn't going to help so much in finding, how x to the 4th changes with a tiny change in x. You're not going to be able to draw a really helpful diagram of that, which is why we start to need more rigorous definitions of how we're going to define what we're calling the derivative, and then we can, relax and use our symbols and stay away from, 182-dimensional diagrams to try to figure out what the derivative of x to the power of 182 is. So just a fun example, little detour into calculus, what we were talking about. This 2x, this is dx squared dx. It's how x squared changes with respect to a tiny change in x. So there's some calculus for you. Let's erase this beauty and get on to the next comment. And that's, I hope I explained that all right. And if you didn't really follow, then blame me. Do not blame yourself. I haven't done that demonstration on the channel before, so just a quick peek. I hope it was helpful. And again, the point is just that those basic understandings, our basic understanding of things, can be helpful, can be intuitive, good place to start. But sometimes we need to come up with more general definitions of things with a bit more rigor so that we can apply it more generally to cases that might be more difficult to intuitively understand. All right, next question. And thanks again for that great comment. Osama Kamal Adhami says, please tell me how to solve these relatively prime. I think, so you want to know which pairs of these numbers are relatively prime. Instead of looking at this as 2 separate questions, let's just take a look at all of the numbers together. 21, 34, 55. 21, 34, 55. And then the other 3, 14, 17, 85. 14, 17, 85. This is on my video about relatively prime numbers. Yeah. So this is really cool. Remember, a prime number is a natural number greater than 1 whose only factors are 1 and itself. We say that 2 numbers are relatively prime or co-prime if their greatest common factor is 1. So they got no factors in common except for 1. Those are relatively prime numbers. Pretty cool idea. Let me take a sip of tea. Good stuff. All right, so which of these numbers are relatively prime? We're going to look at all of them. Nice thing, all we got to do is do some factor trees to find prime factors. Because if 2 numbers have a common factor greater than 1, then they will have a common prime factor. So we just got to look at their prime factors. If they have no prime factors in common, they're relatively prime. Otherwise, they are not relatively prime. So let's jump in and see how this works out. 21 prime factor, factors into 3 times 7. Those are both prime, we're done. 34, prime factorization, 17 times 2. Those are both prime, so we're done. 55 factors into 5 times 11. Those are both prime, we're done. 14 factors into 2 times 7. Those are both prime, we're done. 17 is prime, we're done. 85 factors into 5 times 17. And those are both prime, so we're done. Bunch of easy factor trees here, and you know what? Just because it'll take a while, I won't even write it out. You can see from the factor trees what numbers are going to be relatively prime. The numbers that have no prime factors in common the numbers that have no prime factors in common are the ones that are relatively prime. For example, 21 and 34 have no prime factors in common. 21's got 3 times 7, 34's got 17 times 2. They've got no factors in common, no prime factors in common, so the greatest common factor of 21 and 34 must be equal to 1, and thus they are relatively prime. And I guess it's a quick explanation to why we only have to look at the prime factors. If they're, suppose the greatest common factor of two numbers is, or just suppose that a common factor of two numbers is a, right? A has some prime factorization, so that prime factorization that a has is going to have to be part of the prime factorization of the number it's a factor of. For example, let's see, 34. Do I want to do 34? No. For example, 12, right? 12, one of 12's factors is 4. 4 has prime factors of 2 times 2. So these prime factors are going to have to show up in the factorization of 12 as well, which they do. Its prime factors are 2 times 2 times 3. So you just got to look at the prime factors. That explanation might have been a little bit rushed or unclear, but that's a quick explanation. Look at the prime factors. If two numbers have prime factors in common, like 55 and 85, they got a factor of 5 in common. Their greatest common factor isn't 1, so they're not relatively prime. Whereas 34 and 55 have no prime factors in common, so they are relatively prime. All right, I'll erase a little bit of that, and we'll move on to the next comment. I'm not sure how many more we got to look at, but we are looking at 38 minutes right now on the video. So let's keep on pushing. Let's see, what do we got? We've got Traptown, second channel, said, I enjoyed your video. Keep it up. Would you like to be YouTube friends? Thank you for watching, and thank you for commenting, Traptown. I think, if I remember correctly, your comment was in my spam inbox, and I had to approve it. It does look like a spam comment. Looks like one of those comments people would copy and paste onto different videos. I will say, though, I get a lot of comments in my spam inbox that YouTube just sends straight to the spam box that are not spam. If someone just says, thank you, great video, marked as spam, where it's pretty clear that it's not. It could be from like a regular viewer who I know actually watches the lessons, so it's not a spam comment, and YouTube just puts it in the spam folder. Annoying. On my music channel, I used to be really rude to spam comments. I would be quite the smart ass. I don't know if ass gets me demonetized on YouTube these days. I don't usually push the boundaries that much. Although, fun fact, I did a video on radicans and talking about what is a radical, the symbol, the radical symbol, square root symbol, and that was demonetized because it said radical in the description and in the title. It was later reinstated for monetization, but I thought that was interesting. Anyways, so the spam comments, yeah, on my music channel, I was really rude to spam comments, because they're spam. So, you're not actually giving me any time. You're typically just trying to promote yourself. So I'm just going to sort of use your comment as practice for humor, to get a nice joke in. I don't do that on my math channel because the point is to just teach people math. I'm not here to roast people in the comments. Yeah, if someone else a while ago asked me about doing a collab in the comments, and I gave him a big long response. I was looking back at this the other day, and I was like, man, that's kind of I just gave him such a long response telling him how I would recommend going about a collaboration project, how I would recommend approaching someone for a collaboration project, which is mainly, for one, don't comment on their YouTube video. Send them an email or something, and come with an idea. Why do you want to collab? What value are you bringing? What do you think you two could do together that would be a good thing to do, a good product, a good video? Why should you work together? To me, being YouTube friends would probably mean a collab, so Traptown Second Channel, if you want to collab, send me an email with your idea and we'll see about it. And if your comment was not spam, then I'm sorry for lumping you into the spam conversation. But I'm pretty sure your comment was in the spam inbox and I'm suspicious, so. All right, next question. Charles, and again, I'm sorry about the last name, if I'm pronouncing any names bad. I'm not going to not try to pronounce your last name. I'm going to go for it. Charles Amoforduoh asks, how do you find the center of the tree? Yes. A question I don't really know the answer to. I'm not very familiar with centers of trees, haven't studied them much. I was looking into the definitions a bit, so I could blab on it a little bit, but don't take what I say as gospel. Consider this two boys in a classroom talking about trees who maybe don't know what they're talking about, talking about centers of trees. So from what I understand, the center of a tree, here we've got a beautiful tree graph. Look at this great variety of math we get in a video like this. We got set theory and combinatorics and calculus and algebra and graph theory. What a fun Christmas Eve. The center of a tree is basically centered in a longest path of the tree. So here, our longest path has a length of 1, 2, 3, 4, right? Going across here. So in a path, in a longest path of a tree with even length, the center of the tree is the vertex in that path. So if we just say, let's just say the vertex in the path V1 such that the number of vertices preceding it is the same as the number of vertices following it. So, for this tree, this is our longest path, so the center of the tree is this vertex. It has 2 vertices preceding it in the path and 2 vertices following it. That's why it's a center, or the center, rather. It's the center. If the path has an odd length, if the longest path has an odd length, so, for example, now our longest path has length 1, 2, 3, 4, 5. The center has to be defined slightly differently. It's the pair of vertices, V0, V1, these vertices here, such that there's the same number of vertices preceding V0, 1, 2, as there are following V1 in the path, is what we're talking about, 1, 2. That's what I understand the center of a tree is. And that's about as much as I can give you. So I'm not sure if that answers your question. I assume you wanted something a bit more of a thorough discussion, but there's a little bit about centers of trees. Oh, another train blows its horn. From what I understand, of course, a longest path in a tree isn't necessarily unique. That's why we're saying a longest, right? So we could 1, 2, 3, 4, 5. Here we've got 2 longest paths in the tree, and we can sort of see at a glance that the center vertices are still the same. So that would be, a fun little exercise to prove of what I believe is true, is that the center of a tree is unique. So, if you have 4 longest paths in a tree, they all have the same center. The center is always going to be the same vertex or pair of vertices. And so that's where I'll leave that. Again, don't take that as gospel. I was just briefly reading over definitions the other day, and that's what I believe the center of a tree is. So that's a little bit about centers of trees. Sorry, I can't provide you something more thorough right now. We might do a more thorough discussion of centers of trees in a later video. On to the next comment. What do we got? Might do, how many more was I thinking I was going to do? 1 or 2 more maybe? What do we got? Yes, one of the regular viewers, Siddha vinayak, Acharya, asked, in a response to one of my comments, yes, sir, why don't you make a video on limits and derivatives? I love calculus. Limits and derivatives are really cool. But I will say it's intimidating, picking where to start. I don't do all of my lessons in sequence. I kind of teach what I feel like teaching, because it's not just people on the channel that are going to watch them. Someone could search for a video that you might typically find halfway through a calculus course, and they could see that I've done that video. They'll jump to the video, they'll be ready to go. But even still, it's tough to pick, where do I start, with limits and derivatives? What should the first video be? And then on top of that, there's the pressure of making the Wrath of Math lesson on limits. It's like, man, because what a cool topic, the lesson on limits should be awesome. And so topics like that are really cool, it stresses me out to make lessons about them. I certainly have made plenty of lessons about topics I think are really cool, but yeah, it's a bit intimidating, exactly where to start, and making sure that I give the content a respectable treatment and a really good job presenting it. In any event, in this lesson, you got some derivatives, you got a little bit about derivatives, so I hope you enjoyed that. But lessons on limits and derivatives, and integrals and all that good stuff definitely coming. But for now, you'll probably see more calculus and probability theory lessons, but more strict calculus lessons, they're on their way. I think about them like every single day and how fun it's going to be. Doing real analysis lessons and stuff. It's going to be a lot of fun, but I can only make so much, so we'll have to wait on that for a little bit. But thank you for your comment. Thank you so much for watching. I know you comment a lot. I really appreciate your support, and thank you for letting me know you'd be interested in seeing videos on that, and they're definitely coming. Okay. Fakhira Izza, is that name going to get me demonetized? It doesn't matter, but asks, why do you use the quadratic equation? This was on my video. We're approaching 50 minutes, fellas, ladies and fellas, gentlemen and gentlewomen. That was on my video on how to prove a number's odd. So I'm almost positive I did not use the quadratic equation in that video. So I'm not sure I understand your question. In the video, what I assume I said, haven't watched it in a while, but I assume what I said was that, what was the video? How to prove a number's odd. The definition of an odd number, so say n is odd if it's equal to 2k plus 1 for some integer k. Just did a cool video about odd numbers. I think that's coming out, not yet. It's coming out soon, but not yet, I think. So this is an odd number. So to prove a number is odd, we just have to prove that it's equal to 2k plus 1 for some integer k. Let's do a quick example. So we can prove that an odd number squared is always odd. For example, let's say we've got an odd number, 2j plus 1. J is an integer. If we square this, it's going to be odd. Let's prove it. We square it. What's it equal to? Well, 2j times 2j is 4j squared. Then we'll have 2j plus 1. I guess I'll write these terms out separately. We'll have 2j times 1. Did I say plus 1 earlier? Sorry if I did. 2j times 1. I'll just go ahead and write both terms out to make this more clear. 2j times 2j, 4j squared. 2j times 1, 2j. 1 times 2j plus 2j. 1 times 1 is plus 1. This is equal to 4j squared plus 2j plus 2j is 4j plus 1 at the end. We can factor out a 2 out of those two terms there to give us 2 times 2j squared plus 2j plus 1. By closure, this is an integer. And so we've written an odd number squared, a generic odd number squared, as 2 times some integer plus 1. And so an odd number squared is odd. As far as you asked, why do you use the quadratic equation? I use the quadratic equation to solve quadratic equations. Equations like this, use the quadratic equation to solve those bad boys. So x is equal to plus a, b, and c are constants. X is equal to plus, not plus or minus. X is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. Beautiful equation, really useful. I've been using the quadratic equation a lot recently in my study of financial mathematics. It's kind of funny, financial math is sort of what I've been buried in for most of this year, like 8 months now. So the math I study the most is not the math you see on Wrath of Math typically. The math I've studied the most is probability theory and financial math. And there's zero financial math on Wrath of Math, and there's a smidge of probability theory on Wrath of Math. But I really look forward to doing more probability theory and definitely some lessons on financial mathematics for actuaries, and that's going to be a lot of fun. So I hope that answered your question. Again, I'm not totally sure what your question was. I was a little confused, but hopefully you found that helpful. If I did in fact use the quadratic equation in that video, I should probably take it down because I don't know why why I would have done that. Who knows? Maybe there's a good reason. Okay, BallzOfBananas on my video on how to find the diameter of a circle from circumference asks another question that kind of confuses me. He asks, what if the circumference is centimeters? I assume that's what you mean by cm, centimeters instead of pi. For the last bit here, I assume this is the last bit. I'll do a couple more maybe. Let me put on my Santa hat. Had to get down to get it. It was under my desk. What if the circumference is cm instead of pi? Yeah, I'm not sure what you mean. Is my mic still attached? Yeah. Oh, that'd be horrible if something bad happens to my mic during this recording. If I lose my audio and video, I ain't doing a second take. This is it. So this is the first take. This is the only take forever. What was the question? Circumference is cm instead of pi. Yeah, so the circumference of a circle, the distance around it, we know is equal to pi times the diameter. So in that video, I said to find the diameter from circumference, you just divide both sides by pi, and you see that the diameter of a circle, if you know the circumference, you can find the diameter because it's equal to circumference divided by pi. And so the units here don't matter. The formula is the same. If the diameter is 5 miles, or if the circumference is 5 miles, if it's 4 centimeters, if it's 3 millimeters, divide it by pi, and your diameter is that number with whatever unit your circumference was in. Because pi in this equation has no units. So your units aren't going to get canceled out. If, for example, you have, let's say that we've got a circumference of 2 pi centimeters. Actually, you seem to kind of want to leave pi out of your question. Your question seemed to be kind of straying away from pi. So let's say that the circumference is 3 centimeters. Then the diameter is going to be 3 centimeters divided by pi. Pi is a little bit more than 3, and so this is going to be a little bit less than 1 centimeter will be your diameter, because pi is a little bit more than 3. So this is going to be a little bit less than 1. So I don't know if that answered your question, but hopefully so. The units do not affect, how you're going to find the diameter from the circumference. As long as you got your circumference with some units that make sense for circumference, then you find the diameter the same way. If your circumference was like 8 pounds squared, I can't think of a context where that would make sense. So that might be a red flag, but who knows? There might be a place where thinking of square pounds as a circumference makes sense. I don't know. Weird stuff happens to be surprisingly effective at times. Okay, one more question. I'm going to do one more. Swati Gannamraju asks, where did 9 go in the set A minus B? Why did that disappear? This was on my video, What is Set Subtraction? Oh man, closing in on an hour. This is the last comment. Whew, it's been fun. I hope you guys have enjoyed the video. What a Christmas Eve extravaganza. Longest video I've ever made, certainly. One of the more fun, relaxed ones, too. Okay, so this is a video about set subtraction. I see the 2 sets in the video we're working with. Hey, I think, what was our first video, was the first comment about sets? I can't remember. I think it was, yeah. So we're right back where we started, a set A. This set A only contains even numbers, 2, 4, 6, 8, and 10. And B, oh, what a horrible B. B, people in college used to bully me for how bad my B's looked. No, they didn't really bully me. They're like, Sean, what the heck is that? I'd have like a B like that. What is that? That's a B. That's a Wrath of Math B. B is the set containing 3, 6, and 9. So you asked, why does A minus B not contain 9? Where did the 9 go? A minus B is simply, this is the set consisting of all the elements in A that are not in B. Anything in A that is in B, we take it out. So all that's left is 2, because 2 is in A, but it's not in B. 4, because 4 is in A, but it's not in B. 8, because 8 is in A, but it's not in B. And 10, for the same reason. We lose the 6, because 6 is in B. Perhaps, oh man, I'm losing my voice, I'm losing it. Perhaps it would be helpful for you to use a Venn diagram for this. Say this is the set A, this is the set B. A contains the elements 2, 4, 6, 8, and 10. Looks something like that. And B contains 3, 6, and 9. We already have 6 there. It's in the intersection of A and B because it's in both sets. When we subtract B from A, all we end up getting rid of is that 6 that they have in common. And so A minus B is this. Get rid of that. You know, you're taking B away from A. And so this is what A minus B is. It's all the stuff that was in A except for any elements in A that were also in B. So I hope that clears it up. Whew, it takes too long to take sips of that hot chocolate, you know, because I got to go slow and steady. And now it's really cold, which is too bad. I haven't had dinner yet. It's like, what time is it? 6, about 8, almost 8:30. I don't know if I'm even hungry. But yeah. Merry Christmas Eve, everyone. Really, you know, I'm sorry that I can't respond to every comment anymore. It was a lot of fun when I could. And again, I'm both grateful and sad that I can no longer, lately I can't respond to every comment. There's just too many and I don't have enough time. I'm too busy with work and with math and all that. And you know, I love responding to comments, but I hope that everyone would prefer, you know, that I spend the time keeping the channel steady, new lesson every other day, and you know, trying to make the best lessons I can to keep growing Wrath of Math. And it's you know, I really love it, and I'm gonna keep on making math lessons until I drop dead and turn to dust. Merry Christmas Eve, everybody. Subscribe for the swankiest math lessons on the internet until that day comes that I am nothing, and I will see you next time.
It's been a long I better calm myself, I'm aging quickly. It's such a long time gone. The place is full of garbage and pictures that were bound to mean nothing, while I'm still bound to something that I can't keep. Colorblind through painter's eyes, I hope to God that nobody will notice the secrets I won't dare to tell are colder than a love you can't hold on to. There's nothing can't help but feel like it's all wrong. I mean, it's never really right. Why do you waste your time? You don't even like them, do you? Do you? You are a blue moon girl. It sucks 'cause he just doesn't deserve you, and I wish that you knew it. I just hope you believe it. There's nothing left to tell, but watch the painting dry while the world's underwater. We're